So the topic today, the title of the notes are the 6 trig functions. And we've already studied 3, and I'm going to briefly summarize what we've said about those 3. First of all, if we have a triangle, a right triangle, and let's say here's our reference angle that we're looking at, theta here, and the hypotenuse is 1, then the side length opposite that reference angle is equal to the sine of theta. So sine of theta is the side length of a right triangle with a hypotenuse of 1 across from that angle. And the other side length is the cosine of theta. So those were the first two trig functions we learned about. And then we learned that the tangent of theta is the fraction sine theta over cosine theta. Now those 3 trig functions that we have, the sine, the cosine, and the tangent, there are reciprocals of each of those. Reciprocal means you flip that fraction over, and there's a name for each of those. So the first one is the cosecant. Okay? We're going to abbreviate it CSC. So the cosecant of theta is defined as the reciprocal of the sine of theta. Okay? So if the sine of theta is 2/3, then the cosecant of theta would be what? 1 over 2/3. But that's the same thing as just flipping the fraction over, which would be 3 over 2. That's what we mean by reciprocal. Okay. The second, well, I guess this would be the fourth. So the fifth one would be the reciprocal of cosine, which is called the secant of theta, abbreviated SEC, which is 1 over cosine theta. And same idea, if you know what cosine theta is and you want to find secant of theta, you just flip the fraction over. Okay. And then the last one is the cotangent, abbreviated COT, which is 1 over the tangent of theta. Okay. So we got the cosecant, the secant, and the cotangent. Okay. And so you're going to have to somehow remember that secant goes with cosine. Sometimes people confuse, they think the cosecant should go with the cosine because they both have the cos, but that's not the case here. The cosecant goes with the sine, and the secant goes with the cosine. Okay. The tangent and cotangent, it's easy for you to remember that they go together. They both have the tangent in there. Okay. All right, so we're going to now look at some examples here that you will see on your homework and things that you want to be able to do with these 6 trig functions. Example 1. We're going to assume theta is between 0 and 90 degrees. So we're just in which quadrant? Just in quadrant 1. So for these examples, we'll assume that. And what I want us to do is to find the 6 trig functions of theta if I'm going to give you one of them. let's say the cosine of theta is 3/4. Okay. So really you only need to find 5 more. Okay, so I tell you one of them, you got to find the other 5. Some are easier than others to find. What's one we can get right away? The secant, the reciprocal of cosine. Okay, so I'm going to list them over here on the left-hand side so we know what they are. So we got the sine, and the reciprocal of that would be the cosine. Sorry, the cosecant. We got the cosine, which we know is 3/4. The reciprocal of that would be the secant, which we flip over and get 4/3. And the tangent, we don't know, and the cotangent. Really, we're only missing, if we find one more thing, we can get them all. What's that one thing we need? We got the sine. Well, if we get the sine, because if we find the sine, the tangent is sine over cosine, and then we can just flip over our answers and we got the rest. So if we can find the sine, then we can get everything else. Cosine and sine are kind of the building blocks of all 6 trig functions. Okay. Well, let's kind of draw out what we know with the cosine. I'm going to, working with the unit circle, just to tie this in with what we were doing yesterday. Working in quadrant 1, I'm going to just draw a triangle in quadrant 1. We don't know what the angle is. Let's call that theta. But what we said yesterday is in the unit circle, the radius of that circle is 1, so the hypotenuse here is 1. And we were given that the cosine's 3/4. So where would I put 3/4 in this picture? The x-axis, right? That's the cosine right there. And we don't know what the sine is. I'll call that y, since the sine is the y value, and I remember that from yesterday. Okay. Now, if I extend this triangle past that circle, let's make a larger version of this triangle. Okay. The large right triangle and the small right triangle are similar to each other. You guys see that? Similar by what? Remember how we showed similarity? And if you have a hard time seeing what I'm talking about, so this would be your small right triangle, angle, angle. They share an angle, and they both have what? They both have a 90-degree angle, and so by angle, angle, those two triangles are similar to each other. Now, for the larger triangle, I'm gonna scale it out. I'm gonna take that small triangle and I'm gonna multiply all the side lengths in here by 4. So that the hypotenuse is now 4, and then the base would be what? What would this length be? 3. If you take 3/4 and multiply it by 4, you get 3. The reason I chose 4 is to get rid of my fraction. Now you could multiply it by anything. When you're scaling, you get to pick what to multiply by if you want to scale it out. So I just wanted to work with integers. That's all I'm doing. And it's a right triangle. I know the base is 3, the hypotenuse is 4. How do we find that third side? Pythagorean theorem. Okay, so I'm going to say 3 squared plus, well, I don't know what variable we want to use. Let's call this z, I guess. Plus z squared is equal to 4 squared, using Pythagorean theorem. And so I get 9 plus z squared is 16. Subtract 9. 16 minus 9 is 7. So z is going to be the positive square root of 7. Okay. So to scale out, we multiply by 4. How do we scale back? Divide by 4. And we're really after what y is, because y is the sine of theta. So if we divide root 7 by 4, we get y. So y is going to be the square root of 7 divided by 4. And now we have the sign. The square root of 7 divided by 4. Now we didn't have to do the two triangles. We could have just worked with the small triangle and did the same thing. And if you worked with just a small triangle, it would look like this. You do Pythagorean theorem with 3/4 squared plus y squared equals 1 squared. And if you solve through this, you will end up with y equals the square root of 7 over 4. It just deals with more fractions. So if you like that better, and you don't want to deal with two triangles, you could do that too. Okay? So I'm just showing you one way, showing you a couple ways. So we know the sine. So what's the cosecant? 4 root 7. But we can't have a square root in the denominator. So we rationalize that denominator by multiplying top and bottom by root 7. You get 4 root 7 over 7. So now we got our sine, our cosine, our cosecant and secant. Now for tangent. Tangent is the sine divided by the cosine. So root 7 over 4 divided by 3 over 4. Okay, different ways to go about this, but one of the ways I've shown you already is that root 7, this is root 7 over 4 times the reciprocal, 4 over 3. You can cancel these 4's out and get root 7 over 3. And then the cotangent is the reciprocal of tangent. So if I flip that over, 3 over root 7, and then multiply top and bottom by root 7, and you end up with 3 root 7 over 7. And now we found all 6 trig functions of this angle. Do we even know what the angle is? No, we didn't need to. Okay, that's all right. So let's try this again. Example 2. This time, I'm going to tell you what the cotangent is. So find all 6 trig functions of theta if the cotangent of theta is 5/3. Okay. Again, we're gonna like the one before. Let's assume we're working in quadrant 1. So if we know the cotangent of theta is 5/3, what else do we get pretty easily? Tangent would be what? 3/5. Okay. What do we do from there? What do you mean plug in 3 and 5? Because tangent sine over cosine, so can't we just put in 3 for sine and 5 for cosine? Sounds tempting, but no. There's a couple reasons why. First of all, do you remember what sine is. If we go back to our definition of sine, sine is a side length of this triangle. Can it be 5? No, why not? Too big. The hypotenuse is 1, so we know that sine and cosine cannot be bigger than 1. Okay? So, and here's another thing, another that you want to understand about tangents. Say we worked with this problem, and I gave you the tangent first. The tangent was root 7 over 3. You can see what the sine and cosine are. They're over 4. We wouldn't know that. But the root 7, it's root 7 over something, and it's 3 over something. We just don't know what that something is. And so that's what we're at right now. We know the sine is going to be 3 over something. I'll put a little question mark there. And the cosine is going to be 5 over something. But we're not sure what that something is yet. But we can figure it out, and we will. Why is it that? Okay, here's why. If I do this, so we have 3 over 5. I could divide the 3 and the 5 by the same number. Let's say x. So I'd get, this is the same thing as 3 over x divided by 5 over x. And so we need to figure out what that x is. Okay. So let's go back to our unit circle. Draw a triangle with a hypotenuse of 1. This is our angle theta. We'd like to know what our two side lengths are of this triangle, because that will give us the sine and the cosine. We're not sure what those are, but what we can do is extend this again. And there does exist some bigger triangle that's similar to what we're working with, that's going to have side lengths of 3 and 5. So you know how you wanted to say the sine was 3? Well, it's not 3, but there is a triangle that has a side length 3 here, and there is a triangle that has a side length of 5 here. Okay? Because when you scale that down, remember, this is going to be 3 over x, and this one's going to be 5 over x. So what did we do? How did we go from the small to big? We multiply by x, whatever that is. So there's some scale factor that we're trying to figure out what that is. Well, let's find out what the hypotenuse of this big thing is. And then we'll see how to go from 1 to that number, and we'll find out that scale factor. Okay, so Pythagorean theorem again. So 5 squared plus 3 squared is the hypotenuse squared. So 25 plus 9, which is 34. So the hypotenuse of that triangle is the square root of 34. Okay. So how do you go from the big triangle back to the small triangle? If I want to go from root 34 to 1, I got to divide by square root of 34. So if I want to go from 3 to this 3 over x, I got to divide 3 by square root of 34. So now we found out what our missing x is, the square root of 34. So this is 3 over the square root of 34, and this is 5 over the square root of 34. So what's the sign? And the cosine. Now, we can simplify that, right? But before we do, let's get the cosecant and the secant. Because what happens when you flip them over? The square root goes to the top, and that's what we want, right? And then we need to go back and fix anything that has a denominator with a square root. So we multiply top and bottom by square root 34 and get 3 square root 34 over 34. And here we get 5 square root 34 over 34. And so we found our 6 trig functions. And so this one was a little different. We had to start differently because we didn't know the sine or the cosine at all. All we were given was the tangent, or the cotangent. We got the tangent that way. And so we had to kind of reason through this to find that that scale factor. Okay. Any questions yet? Yes. So the secant is it comes to these are all ratios of your triangle. So your triangle has 3 sides, right? And if you have 3 sides, or say you have 3 numbers, and you're trying to find ratios between them, how many different ratios can you make? You end up with 6. And let me just show you really quickly how. If you have a right triangle, A, B, and C, and I just make it, how many different fractions can I make with those 3 letters? I can go A over B, A over C, B over A, B over C, C over A, and C over B. And those are the only 6 you can do. And it turns out that each of those represent a different trig function. And so that's where you're just naming them. And later on, we're going to graph each of these and look into that, and they have applications. Okay, but that's where it's coming from. All right, a third example. Okay, now I'm going to relate it to what we were doing yesterday. I want you to find the secant of 135 degrees. Okay, and I'm going to give you a little time to do this one. Try to find the secant of 135 degrees. Okay, did we get an answer? What'd you get? Negative 2 root 2 over 2. All right, let's check. So, I draw my unit circle here. 135 degrees, got to locate that. Here's 0, we're moving counterclockwise. 90, 180. So it's in quadrant 2, actually right in between the 180 and the 90. And so that's 135. And if you look at the difference between 180 and 135, what do you get? 45. So this is a 45, 45, 90 right triangle, and the hypotenuse is 1. And so what is the side lengths? Okay, so root 2 over 2 is what we want, and then we got to respect the quadrants. So the x value is negative root 2 over 2, and this is positive root 2 over 2. So this is the cosine of 135. And the secant is the reciprocal of the cosine. So the secant of 135 is negative 2 over root 2. So if you got that far, you're correct. You just need to simplify it. So to rationalize the denominator, we multiply top and bottom by root 2 and get negative 2 root 2 over 2. And that's what you said. One more step, though. The 2's you can reduce. So if you divide them both by 2, you end up with just negative root 2. Okay. This is a quicker example, right? And an even quicker one is this next one. find the cosecant of 90 degrees. What are we coming up with? Undefined? 0, 1. Okay, I heard 0, undefined, and 1. So let's take a look. All right, so locate 90 degrees. That's at north. This is a unit circle, so the radius is 1. So what's the coordinate of that point at 90 degrees? 0, comma 1. And the x coordinate represents what? The cosine of 90 degrees. And the y coordinate represents the sine of 90 degrees. Now the cosecant is the reciprocal of which one? Sine. So when you have a reciprocal, you in a sense flip the fraction over. So can you give me a fraction that's equal to 1? 1 over 1. And then flip that one over. What do you get? 1 over 1. So what's the cosecant? Cosecant of 90 degrees is still going to be 1. Okay. Now, if we were talking about the, let's just, since we're here, what would the secant of 90 degrees be? In other words, what's the reciprocal of 0? So you think of 0, think of that as a fraction. That's 0 over 1, right? Or 0 over 2. Just pick a fraction that's equal to 0. And then when you flip that over, 0 becomes the denominator. And what happens when when you get that? It's undefined. So the secant of 90 degrees is undefined. Okay. All right, last example here. All right, so here's a triangle with 2 side lengths, and I'd like you to find, let's go with the secant of angle C. Okay, what else do we know about this triangle? Isosceles. How do we know it's isosceles? The base angles are the same, and there's a theorem that we studied a while ago that says that the base angles are the same, then it's isosceles, right? Remember the name of that theorem? The isosceles triangle theorem. Okay. Actually, it's the inverse of the isosceles triangle theorem. Okay. So then, any other? What should we do next? The drop in altitude. Okay. Now, when I drop that altitude and get that 90 degrees, now I have 2 right triangles. Let's call that point D. Okay. But I mean, at least in my drawing, it looks like the length here from A to D is a little shorter than the length from D to C, but is D the midpoint? Why does it have to be the midpoint? So can anybody argue that the left triangle is congruent to the right triangle? If so, why would they be congruent? By what? So triangle ABD, you're saying is congruent to triangle CBD. We have angle A is congruent to angle C. What else do we have? So BD is congruent to BD. Angle BDC is congruent to angle BD8 because they're both 90 degrees. So this is side, 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 or side angle side, or what? Angle, angle side. All right. All right. So because the two triangles are congruent, we could say AD is congruent to DC by CPCTC. So what are those side lengths? 15. Okay. So how is the hypotenuse 10? So, oops. If we have a base of 30, there's no way to connect the two side lengths of 10, is there? So we're going to have to modify this problem a little bit. Let's change the 10s to 20s, okay? Oops. All right. Now we could do it. Okay. So what now? Do we even need to know this side or not? I don't think we do. But here's what we want to do, guys. We want to relate it to a similar triangle with a hypotenuse of 1. Same angle C. Okay. So how did I go from 20 down to 1? Okay, so then what's the base length going to be? 15 over 20, 3/4. And guys, what's the significance of the 3/4? What's that equal to? That's the cosine of angle C is 3/4. Okay. So what's the secant? Yeah. So here, if we have a right triangle with a hypotenuse of 1, the side opposite is the sine of that angle, and the side adjacent to it is the cosine of that angle. And so we know these two triangles are similar by angle, angle. And so we're just scaling it down so that we have a triangle with side length or hypotenuse of 1. So if this is 20, I need to divide by 20 to get the hypotenuse of 1. So I took the 15, divide that by 20 to get the new side length here, scaling it down. And so now that's how I'm getting the cosine. And then you get the reciprocal for the secant. Okay. All right. So that's the end of our notes.